understand. Then we can able to start doing the proof of the exponential Fourier series coefficient for the x of a t signal. Okay, what are the conclusions here from this discussion we can able to made in the sense, after performing the time scaling, the time period and the fundamental frequencies will be changed. Okay, so again I am writing here x of t is having the Fourier series coefficient is Cn. Now we need to know how to get the fundamental Fourier series for the time scaled version of the x of t, that is x of a t, that is also Cn only. For that we will see the proof now. Okay, so now I am writing the exponential Fourier series coefficient of x of t that we have represented with Cn, that is equal to, the formula is given by 1 by t integral t is changing from 0 to t x of t e power minus j n omega naught into t dt. This is the formula for the exponential Fourier series coefficient of the signal x of t. Okay, how this formula is written, that I am explaining now. Listen clearly. X of t is a periodic signal and it is having the time period is capital T and its fundamental frequency is omega naught. Okay, so x of t is having the fundamental time period is capital T and fundamental frequency is omega naught. These two are related to x of t. Okay, so that's why those two are included in the formula of the Cn, are the exponential Fourier series coefficient of the x of t, that is equal to 1 by t integral t changing from 0 to t x of t e power minus j n omega naught t dt. So 1 by time period of the signal x of t integral time, we need to take the integral over one period of the signal x of t, and this is place for the signal for which we are calculating the Fourier series coefficient. After writing the signal, we need to write e power minus j n. This is the fundamental frequency of the signal x of t. Everything is related to x of t only, because this is the Fourier series coefficient of the signal x of t. So 1 by time period of the x of t integral over the time period only we have to take, and for which signal we are calculating the coefficient, that signal has to be written. After that, e power minus j n, this fundamental frequency is for the x of t only, t dt we have to write. Now if you try to write the Fourier series coefficient formula for x of a t, for x of a t if you write, it is also the periodic signal. So in the same manner I will try to write the equation for this one. 1 by time period of the signal x of t I have to write here. 1 by time period of the signal x of t is represented with capital T, but here I need to write the time period of the signal x of a t. Previously we have seen the time period of the signal x of a t is t1, that is t by a. So in this way you will get integral t is from 0 to t by a I can write, and I am calculating the coefficient for x of a t. This is the place for the signal for which we are calculating the coefficient. That's why x of a t e power minus j n. Here I need to write the fundamental frequency of the signal x of a t only, that I know already, that is a into omega naught into t dt. So the x of a t is having the fundamental time period is t by a and fundamental frequency is a into omega naught. That's why I have written the equation is like this. Okay, then this a t I am taking as the new variable k, and do the differentiation for this one. A is constant, dt is equal to dk, and from this I can write dt is equal to dk by a. Okay, then lower limit for t is 0. This is the lower limit for t. So if you substitute here, k is also I will get as 0 only. The lower limit for k is also 0, because a into 0 is 0. Now upper limit for t I got as capital T by a. So it is equal to capital A, k is equal to, if you substitute the upper limit in this equation, a into capital T by a will be cancelled, and k is equal to, you will get capital T. So in this way you will get. Okay, so now substitute in this one, replace the variable t with k. So finally what we will get means it is equal to, that means exponential Fourier series coefficient of x of a t, I will get like this. It is equal to a by capital T integral k is from 0 to capital T. Okay, now I am writing the limits for k. So k is from 0 to capital T, x of k e power minus jn a into omega naught, and the variable t is nothing but I can write now k by a, and dt is nothing but dk by a. So a will be cancelled, this a and this a will be cancelled. Now this entire thing is looking like again Cn only, because 1 by t integral some variable is there that is changing from 0 to t, and x of k e power minus jn omega naught k dk. If you observe the Cn formula, in place of small t here k is there. Small t is the independent variable changing from minus infinity to plus infinity, and k is also the independent variable changing from minus infinity to plus infinity. So in the formula there is no change. That means it is also giving the expression of the Cn only. So what is the conclusion here? X of t is having the Fourier series coefficient is Cn. X of at is also having the Fourier series coefficient is Cn only. But where are the changes are occurring due to the time scale version means the time period is affected and the fundamental frequency is affected. Time period is changed to t by a and fundamental frequency is changed to a times omega naught. But the exponential Fourier series coefficient is same. So this is the thing. This is about time scaling property of the Fourier series. Now f of t is equal to sine of omega naught t, and draw the magnitude and phase spectrums of this particular signal. Already we know f of t is equal to sine of omega naught t, because it is in the continuous domain, it is a periodic signal. So f of t is equal to sine of omega naught into t, and this one we can able to write it is like sine theta. So sine theta means we can write e power j theta minus e power minus j theta by 2j. By comparing